We've learned about tangent vectors. We've also talked about unit vectors. We're going to combine the two ideas here, and we're also going to relate it back to a visual that we might remember from Calc 1. Remember that in Calc 1, the derivative at a point can be interpreted as the slope of the tangent line to the graph at that point. Well, in Calc 3, we have a really similar visual. With a vector valued function, the derivative will create a tangent vector to a curve represented by the function. The curve on the screen is represented by a vector function. It's the white circle. The vector function generates the blue vector. That's a position vector. It's pointing to an orange point on the curve, and the green vector is the tangent vector at that point. If our curve, which it is represented by r of t, given by cosine t in the I hat direction, sine t in the j hat direction, then the derivative of that vector function looks like negative sine t I hat plus cosine t j hat. We can use this to find a tangent line just like we did in Calc 1. So if we want, we can find the line tangent to the curve at t equals pi over 6. To do that, we need to find the slope at t equals pi over 6. Which means we just plug pi over 6 into our r prime function that we've generated for the tangent vector. So we'd have negative sine at pi over 6, which is just negative 1/2 I hat. And then we'd have cosine at pi over 6, which would be root 3 over 2 j hat. Now what I mean by this vector is essentially slope is that this is the vector that our tangent line should be parallel to. Now on the screen, again, we have the vector function in white. We have the actual vector that's mapping out that curve in blue. We have the point that comes from pi over 6 going into our function in orange. And then we have our vector function, r prime, starting at the point on our curve and ending at the point that comes from, starting at r pi over 6, it ends at r prime plus r at pi over 6. To find the tangent line, we need two things. We need a point on the line, and we need a vector that's parallel to that line. So to generate that line, we're going to use the point that comes from r with pi over 6 plugged into it. And then the vector is going to be that tangent vector. We'll use our equations, parametric equations. So we would have x equals, well, the x value from r with pi over 6 plugged into it, we still have to find that. So let's go ahead and do that. R at pi over 6, that would look like cosine at pi over 6 in the I hat direction, plus sine at pi over 6 in the j hat direction. And we can see that matches up with our graph. In the x direction, we're traveling root 3 over 2. In the y direction, we're traveling 1/2. So for the x equation of our parametric equations of the line, I would have root 3 over 2 plus t times the x component from the derivative vector. So plus negative 1/2 t, and then y would look like 1/2 the value of the coefficient in front of the j hat vector for r at pi over 6 plus t times the j component from the tangent vector. It would be plus root 3 over 2 t. Now these are the parametric equations for the line. It's not necessary to write it this way, but I figured we ought to. Notice there is no z equation. When we did parametric equations in 3D, we did use a z, but this is a 2D situation, so z is not involved here. And if we wanted to graph this, we would use the point on the curve, and then our line would be parallel to that tangent vector. And in this case, it's right on top of that tangent vector, not just parallel to it. Now, one thing to keep in mind if you are looking at finding the line tangent to a curve like this, if you want to plot this tangent vector, so let's talk about this for a moment, r prime of t looks like -1/2 I hat plus √3/2 j hat. That vector, if we plotted it as a position vector, it would actually look like this. But if I want it to look like it's tangent to my curve, I need to plot that vector where it starts at my point on the curve, r at pi/6, and then from that value I add this slope. So how do I get the terminal point of my tangent vector in this case? What I do is I create the vector by starting with the values from r at pi/6. So I'll have √3/2 in the x direction, 1/2 in the y direction, and I add to that the components from the tangent vector. So plus the -1/2 in the x direction and plus √3/2 in the y direction. That would be the terminal point for the green vector here. We know how to find a tangent vector. We know how to find a unit vector. We're going to combine those ideas here to create something called a unit tangent vector, which we call capital T. Ooh, that looks like an I. Capital T. And it's basically the derivative of our vector function r divided by the magnitude of that derivative of the vector function r. So let's do a couple of examples. If r is the function we were working with in the last example, then we know r prime looks like -sine t in the I hat component and cosine t, j hat component. Then we'd need to calculate the magnitude of that. So we take each of the component functions and square them, add them together and square root. That gives us positive sine squared t plus cosine squared t inside of a square root. And sine squared plus cosine squared is 1, so we're really looking at the square root of 1. And we were calculating the magnitude of that r prime vector. We just found the magnitude is 1, so spoiler alert, that was already a unit tangent vector, but just to be thorough, we could say that t is equal to r prime divided by the magnitude of r prime, which would be -sine t I hat plus cosine t j hat divided by 1. Or we don't even have to write divided by 1. Let's try another example here. This time we're looking at u of t. So to generate this unit tangent, we do need to calculate u prime. Then I need to calculate the magnitude of u prime, taking each component, squaring it, and then adding them up. Multiplying out my binomial squared using our pattern. my 2 times 6 times 2, my 4t. So then I can write this in descending order. And I can try and simplify this if possible. I happen to know that there's a factor of 4 in each one of these numbers, and if I factor a 4 out, then I can write this, I almost forgot my 4 exponent there, but I could write this as 2 times the square root 36 t to the 4th plus 9t squared plus 6t plus 10. So that's the magnitude of this vector u. Now we can create the unit tangent simply by dividing the original vector, the derivative of the vector u prime, by the magnitude. So we'll have 6t plus 2 I hat minus 12t squared j hat plus 6 k hat, all divided by this magnitude that we just calculated. Now this unit vector, capital T, that we're finding, it is actually a vector function itself, and it will generate a unit vector that is tangent to the curve u at any parameter value for t.